Hello everyone and welcome back to the course. In today's lesson, we are going to learn a new operation between functions. Today, it's about function composition. So, off we go. Let us consider two functions, f and g, where f is a function defined from x to y, and g is a function defined from y to z, such that the range of f is equal to the domain of g. If those conditions are satisfied, then we can define a new function, h, which goes from x to z, such that h of x is equal to g of f of x. And we denote this in the following way: g composed with f of x. Thus, for being able to define the composition of functions, it's necessary that the range of f is equal to the domain of g. Otherwise, it won't be able to be properly defined. Let us consider the following two functions: f of x equal x squared and g of x equal x plus 2. Then, f of g of x will be equal to x plus 2, x squared. And g of f of x will be equal to x squared plus 2. Let us take two other functions, f of x equal the square root of x and g of x equal 4x. Then f of g of x will be equal to the square root of 4x, which can be simplified as 2 square root of x. And if we do g of f of x, this will be equal to 4 square root of x. As you can notice, function composition is not commutative. Now let us consider the following two functions: f of x equal x squared and g of x equal the square root of x when x is greater than or equal than 0. Then f of g of x will be the square root of x squared, and that is equal to x. And if we do the other way around, g of f of x, that will be equal to the square root of x squared, which is also equal to x. Now, something that we noticed in the previous example was pretty remarkable, and that was that f composed with g was equal to g composed with f, and they were equal to x. When that happens, we say that f and g are inverse functions. The following represents a list of basic functions and their inverses. If f of x is equal to ax plus b, then x minus b divided by a represents its inverse. If f of x is equal to x to the n, then the nth root of x is its inverse. Log b of x has as inverse b to the x, and the special case natural logarithm of x has e to the x as its inverse. Now, the trigonometric functions sine, cosine, and tangent have as inverses arcsine, arccosine, and arctangent, respectively. And cosecant, secant, and cotangent have as inverses arccosecant, arcsecant, and arccotangent. I invite you to graph all of the functions that I just mentioned so you can start getting familiar with them. In this course, we are going to use each and every single function that I just mentioned, and we are going to learn every single property about them. Now, given a graph, how do we determine if it has an inverse? Well, for this case, we use the horizontal line criteria. This criteria is based on drawing a horizontal line, and if this horizontal line intersects the graph of the function more than once, then such a function does not have an inverse. For example, if we consider the graph of this function, we can draw a horizontal line which cuts the function in 3 points. Thus, this function does not have an inverse. Nevertheless, if we take the function f of x equal x cubed, as you can see on the graph, if we try to draw a horizontal line that intersects the graph, this line does not cut the function more than once. So this function has an inverse, which is actually the third root of x. Finally, we are going to introduce 3 concepts that allow us to determine if a function has an inverse or not in an analytical way. Those concepts are the concepts of injection, surjection, and bijection. We say that a function is injective or one-to-one if and only if we can take 2 output values, y1 equals to f of x sub 1 and y2 equals to f of x sub 2. If y1 is equal to y2, then necessarily x1 has to be equal to x2. A function f defined on the sets x, y is said to be surjective or onto if and only if for each element y in y there's an element x in x such that f of x is equal to y. In other words, if the codomain of this function is equal to the range, then f is onto. Finally, a function is said to be bijective if and only if f is onto and one-to-one. There's a special result on this, and it says that f has an inverse if and only if f is bijective. So bijection is a concept that allows us to determine if a function has an inverse or not in an analytical way. We just have to prove that the function is onto and also one-to-one. And if those 2 concepts are satisfied, then the function f is bijective, and therefore it has an inverse. For example, if we take again the function f of x equal x cubed, we can notice that the range is equal to the codomain. Thus, the function is surjective. Now, we used the horizontal line criteria for determining that there aren't 2 values of x with the same output. Therefore, this function is one-to-one. Thus, x cubed is bijective. Thus, f has an inverse. Well guys, this is all for today. Thank you very much for following this video until its very end. I'm really proud for what you have made so far. And as usual, you have to put your knowledge into practice. So try to determine if the following functions are invertible or not. So well guys, as always, see you in the next lesson.